Welcome to the Cow Corporation's series of videos about software engineering. The topic of this video is a critical section of code. Before proceeding, make sure that you have already watched these other videos first. Normally, a static variable is shared by all threads. However, you can mark a static variable by the thread local keyword to cause each thread to have its own instance of that variable. In terms of syntax, this source code would be okay. These threads A and B both have access to the shared static variable, so they both can increment it. But after C++ code is compiled into the computer's machine language, it requires a set of several machine language instructions to implement this gi shared equals gi shared plus 1 statement. Because we haven't done anything special to synchronize their access to that shared variable, it's possible that thread A's set of machine language instructions might get interleaved with thread B's set of machine language instructions. So the final result of this multi-threaded software is unpredictably unsafe. What we need to have is that when this gi shared equals gi shared plus 1 statement gets compiled, its resultant set of machine language instructions gets treated as atomic, at least in the sense of how it uses shared variables or resources. That way, our thread's machine language won't interleave with another thread's. We say that this gi shared equals gi shared plus 1 code fragment is a critical section. To accomplish our goal, extra source code will be programmed immediately before and after the critical section to enforce these critical section properties. To get the atomic behavior that we need, a thread's execution within its critical section should be mutually exclusive execution. We might abbreviate this property as mutex, although that mutex abbreviation sometimes also refers to the synchronization primitives that are enforcing this property. If one thread's execution is still in the middle of a critical section, at the time when the operating system context switches you into another thread, then that other thread is prohibited by the synchronization primitives, prohibited from entering into the beginning of that critical section. A good multi-threaded program makes it impossible for threads to deadlock. Deadlock can occur if two threads are both blocked, each waiting for the other thread to do something. Live lock is the name of another problem, which is the same each waiting for the other problem as deadlock. The difference being deadlock uses blocking, whereas live locked threads repeatedly wake up to check a condition that never gets satisfied. Dining philosophers is the name of a theoretical problem which demonstrates how deadlock can occur between more than two threads. In the dining philosophers problem, each thread is like a philosopher person eating at a round table, and there's one chopstick between each pair of philosophers. If everybody picks up the chopstick on their left, then nobody will be able to subsequently pick up the chopstick that was on their right, and so the whole system deadlocks without anybody being able to eat. Access to a critical section must be fair in a probabilistic sense. If one thread is always the lucky one to get access while another thread indefinitely waits, then the repeatedly unlucky thread can starve. Fairness is often enforced by doing some form of turn taking.